Mode characteristics. Today let us go through these mode characteristics. Myself Dr. V. Vijayashree Bolsetti, Associate Professor, Department of Electronics and Communication Engineering. So what are the mode characteristics? So we have seen different modes that are propagating through the rectangular waveguides, transverse electric modes and transverse magnetic modes. So some of the characteristics of those modes like guided wave impedance or waveguide length, wavelength and phase velocity, group velocity of the mode that is propagating, let us see in this mode characteristics. So at the end of this lecture, the student will be able to define and obtain the relations for phase and group velocities, wavelength and impedance relations. So first let us see what is a guided wavelength. So guided wavelength is usually notated with representation lambda suffix g. So lambda g represents the guided wavelength. So how this wavelength, guided wavelength is defined? So it is defined as the distance travelled by the wave to undergo a phase change of 2 pi radians. So for example, if you consider a sine wave is to propagate, so the sine wave has a phase change of 0 to 2 pi, and to undergo this one complete cycle to a phase change of 2 pi, what is the distance it is travelled? So this distance we are calling it as the guided wavelength, lambda g. So how we are expressing this lambda g? Lambda g is equal to 2 pi by beta. So as for continuation of the last session, we have equated this as number 8. So lambda g is equal to 2 pi by beta, where beta is the phase constant and it is undergoing a phase shift of 2 pi radians. So now let us see some of the important properties of this guided wavelength. So the wavelength in the waveguide, when you consider a ordinary transmission, that means in a free space, and when you consider the propagation in a waveguide, so there is a lot of difference between the propagation in the free space and the propagation in the waveguide. So the wavelength in the waveguide is not same as the wavelength in the free space. That means suppose if it is free space, it may be lambda g, and if it may be in the guided wavelength, it may be some other lambda. So that means it may be occupying some more distance to have a phase change of 2 pi radians. So there is a difference between the guided wavelength in the waveguide as well as the wavelength in the free space. So as the wave propagates in the waveguide, so the generally this guided in the waveguide, the wavelength is greater than the wavelength while it is propagating through the free space. Okay, propagating through the free space. So lambda naught is the wavelength in the free space and lambda g is the wavelength in the waveguide. If you consider like this, then always this lambda g is greater than lambda naught, greater than the free space wavelength. So these are some of the important properties of the guided wavelength. Next let us define one more important mode characteristic, that is phase velocity. Phase velocity. So coming to this phase velocity, we represent the phase velocity with v suffix p, and it is defined as the rate at which the wave changes its phase in terms of the guided wavelength, and it is as it is represented as Vp. If we can define this Vp as a product of lambda g and f. So here this is the guided wavelength, this guided wavelength we are representing generally as a lambda g, and so the phase change that occurs in terms of the guided wavelength, we can define it as the phase velocity. So what is Vp? Vp is equal to lambda g into f. So if you multiply this lambda g f with 2 pi both numerator and denominator, then we are going to get 2 pi f into lambda g by 2 pi, and already we have defined. So this lambda g by 2 pi in the guided wavelength, that is lambda g is equal to 2 pi by beta. So from this we can get this lambda g by 2 pi is nothing but equal to beta. So this implies beta is equal to 2 pi by lambda g, and here we have the relation lambda g by 2 pi, so we can write it as 1 by beta, and 2 pi f can be written as omega, angular frequency omega. So the phase velocity Vp is equal to omega by beta. Now we know that already we have defined in our previous session what is the propagation constant gamma. So the gamma is defined as a phase constant in terms of the phase constant and the attenuation constant, where alpha it is the attenuation constant and beta is the phase constant, and this gamma is represented as the propagation constant. Okay. So this propagation constant is expressed in terms of alpha plus j beta. Also from the equation h square is equal to a square plus b square, we have derived this gamma is also equal to n pi by b whole square plus m pi by a whole square minus omega square mu epsilon. So this is actually the gamma, and from this gamma now let us obtain what is this phase constant beta, so that we can get a relation for the phase velocity in terms of Vp is equal to omega, and if we substitute the beta in terms of cutoff frequency and in terms of operating frequency, in terms of guided wavelength and all. Okay. So now let us see how we are going to obtain beta from this. So for at the propagation, that means the condition for propagation is this alpha should be equal to 0. Alpha should be equal to 0. So the wave propagates at alpha is equal to 0. As alpha is equal to 0, while substituting in gamma is equal to alpha plus j beta, simply we get gamma is equal to, as alpha is 0, gamma we can write it as equal to j beta. Okay. So what we are going to get, as gamma is equal to j beta and there is a square root, so let us square on both sides. So we are going to get j beta whole square is equal to n pi by b whole square plus m pi by a whole square minus omega square mu epsilon. Okay. So now here it is j beta whole square. Okay. So simply we can write it as j square beta square, where j square is minus, so we'll get it as minus beta square. And what about this term, n pi by b whole square plus m pi by a whole square? So this also, while deriving the cutoff frequency, we have considered that this term should be equal to omega c square mu epsilon. So let us see that as this term is equal to omega c square mu epsilon, let us substitute this omega c square mu epsilon in this place, and so let us obtain what is this equation. So that is j beta whole square, we can write it as minus beta square. This is minus beta square, and this term is replaced with omega c square mu epsilon minus omega square mu epsilon. As minus beta c square is this relation, so simply we can alter these terms, these values, so to get the beta square. So therefore beta square is equal to omega square mu epsilon minus omega c square mu epsilon. So beta can be obtained as a square root of this term. Okay. So beta is nothing but root omega square mu epsilon minus omega c square mu epsilon, and already we have defined the phase velocity Vp is equal to, got it as omega by beta. So let us substitute this beta in the phase velocity. Okay. So if we take this mu epsilon as common in this, we are going to get mu epsilon omega square minus omega c square. So let us substitute this equation 10 in the relation phase velocity. So in 9, so what we are going to get, Vp is nothing but equal to omega by, in place of beta we substitute root mu epsilon omega square minus omega c square. Here this omega means, omega is nothing but we can call it as the free space angular frequency. Okay. So we can also represent this omega as 2 pi f naught free space frequency in terms of free space frequency. Okay. So if you take omega square common from this term under the square root, then we are going to get this term becomes omega by, if we take omega square mu epsilon as common, it becomes 1 minus omega c by omega whole square. Okay. So now here in the root we have omega square and in the numerator is omega. So root omega square can be treated as omega, and so this omega get cancelled, and so we are going to get the phase velocity Vp is equal to 1 by root mu epsilon 1 minus omega c by omega whole square. Okay. So and this 1 by root mu epsilon is nothing but equal to the velocity of light c. So we can write 1 by root mu epsilon can be written it as c. So the phase velocity Vp is equal to c by root 1 minus omega c square by omega square, or this omegas can also be written in terms of the 2 pi f, because always omega is nothing but we can write in terms of the f naught, or f can be considered it as the free space frequency, and omega c we can write it as omega c is equal to 2 pi fc, where fc is the cutoff frequency. So the same expression we can express in terms of fc and f naught. So the phase velocity Vp is equal to c by root 1 minus fc square by f square, or we can also call it as f naught square. And similarly we have the relation that lambda is equal to c by f, as the frequency and the wavelength are inversely proportional. We can write that f as c by lambda. So if you use this relation, that means we can invert these terms in while writing in terms of the lambda. So simply we can get Vp is equal to c by root 1 minus lambda naught by lambda c whole square. Okay, lambda naught by lambda c whole square. Okay, anyhow we can also express this as c by root 1 minus lambda naught by lambda c whole square. So this is the phase velocity what we have defined, and we got to obtain the relation for the phase velocity in terms of the frequency and in terms of the wavelength in the equations 11 and 12. Okay. So now we have defined this phase velocity Then we go for another more characteristic, that is group velocity. Okay, so how we define this group velocity? So the group velocity is defined as the rate at which the wave propagates through the waveguide, and it is given by Vg, and it is represented by Vg, V suffix g, and this group velocity can define it as the change, that is d omega by d beta, where phase velocity we have represented it as omega by beta, and the group velocity is d omega by d beta. So let us represent this group velocity, and to obtain this d omega by d beta we need to derive the expression, that is beta. Beta we can express it in terms of omega and omega c. Okay, so that is beta we have taken it as equal to root mu epsilon omega square minus omega c square. We have this relation. So by using this relation, which is related, beta and omega are related, so if you differentiate this equation we can get this group velocity. So let us differentiate this equation with respect to omega c square. Okay, with respect to omega. Okay, then if you take this equation and differentiate it with respect to omega, so the equation I will write here, beta is equal to root, we write it as to the power, so simply mu epsilon omega square minus omega c square whole power 1 by 2. That square root can also be expressed in terms of whole power 1 by 2, and using this relation we have differentiate this equation with respect to omega on both sides. So what we are going to get, d beta is equal to 1 by 2 this expression mu epsilon omega square minus omega c square whole power 1 by 2 minus 1, that is minus 1 by 2, and then the differentiation of this term, that is mu epsilon is constant and the differentiation of omega square is 2 omega d omega. Okay. Now by simplifying this equation, that means this 2 gets cancelled, and this is mu epsilon omega square minus omega c square whole power minus 1 by 2, that means it comes under the denominator. Okay. So this term is in the denominator, it is square root of mu epsilon omega square minus omega c square. So let us see, express this in the denominator, and the remaining term mu epsilon omega d omega. So here we have root mu epsilon and here mu epsilon, so we can simply cancel them and can make this as a root mu epsilon. And also if you take this omega as common in the both numerator and the denominator, then we are going to get the relation between d beta and d omega in terms of the cutoff frequencies. Okay. So what is d beta? So d beta, omega also get cancelled in the numerator and denominator, because we got the expression that it is root mu epsilon omega by root of omega square minus omega c square. Okay. So if you take omega as common from this, so simply we can write this as 1 minus omega c square by omega square, and omega also can be expressed in terms of 2 pi f. So simply we can also write d beta is equal to root mu epsilon by, and here we have the omega, this omega gets cancelled. Okay. So root mu epsilon by root 1 minus f c square by f square d omega, and also this can be written, we can invert this f and f c, we can invert them these terms while representing in the wavelength. Okay. And let us substitute this d beta and d omega. So for group velocity, how we have defined it is defined as Vg is equal to d omega by d beta. That means we want d omega by d beta, so let us take this term to that side. So anyhow, so d beta we got it as root mu epsilon, we can write it as 1 by c, because c is equal to 1 by root mu epsilon. As c is equal to 1 by root mu epsilon, we can write root mu epsilon as 1 by c, root 1 minus f c square by f square. Also this can be expressed in terms that is d beta by d omega is equal to like this, and we need d omega by d beta. So the group velocity can be the inverse of this function. Okay. So the group velocity Vg can be written it as c root 1 minus f c square by f square. So d omega by d beta is equal to c root 1 minus f c square by f square, or that is also equal to this d omega by d beta is nothing but Vg, and we can also express this either in fc by f whole square, or we can also express them in terms of the wavelength. So this f we can write it as c by lambda naught, and fc we can write it as c by fc. So c by lambda c. So we can write Vg is equal to c root 1 minus lambda naught square by lambda c square. So this is the relation for the group velocity. So in the last session, that means in the previously we have defined what is the phase velocity Vp, and now we have obtained the group velocity Vg. So if you take this phase velocity, so this phase velocity we have obtained it as equal to c by root 1 minus lambda naught by lambda c whole square. So this group velocity is c into root 1 minus lambda naught by lambda c whole square. So by observing these two, we can get the relation, that is if we multiply this Vp and Vg, okay, you are going to get Vg into Vp is nothing but equal to c square. Okay. So this term, root term will get cancelled here, and this is nothing but equal to c square. Okay. So the product of the phase velocity and group velocity always results a constant, because c is the velocity of light, always results a constant, and that is equal to the velocity of light whole square. Okay. So Vg into Vp is equal to c square. This is also one of the important relation. Right. So now, so far we have discussed about the guided wavelength lambda g, phase velocity and group velocity. So now let us also define what is the wave impedance, and also let us see what is the relation between lambda g, lambda naught and lambda c. See, we have the relation, that means the phase velocity Vp is equal to lambda g into f. The phase velocity Vp is equal to lambda g into f, where we can write this f is nothing but equal to c by lambda. So simply we can also write it as into c by lambda naught, where lambda naught is the free space wavelength and f is the free space frequency. Okay. So Vp is nothing but equal to lambda g by lambda naught into c, but already we have derived the expression for Vp, and that is equal to c by root 1 minus lambda naught by lambda c whole square. We have this relation. Okay. So what it is going to say, that means these two should be same, and so we can say, as the c gets cancelled on both sides, we can say that lambda g by lambda naught is equal to 1 by root 1 minus lambda naught by lambda c whole square. Or simply we can also say, this implies lambda g is equal to lambda naught by root 1 minus lambda naught by lambda c whole square. So, this is a relation between guided wavelength lambda g, free space wavelength lambda naught and cutoff wavelength lambda c. So, this is one relation, or we can also get one more relation for this. Suppose let us take this equation and inverse this, so that we are going to get lambda naught by lambda g is equal to root 1 minus lambda naught by lambda c whole square. Okay. So, let us square on both sides. So, this indicates lambda naught by lambda g whole square is equal to 1 minus lambda naught by lambda c whole square. Okay. So, by simplifying this, if you take this lambda naught square to this side, bring this lambda naught square to this side, we are going to get 1 by lambda g square is equal to 1 by lambda naught square minus, bringing this lambda naught square to this side, denominator it cancels here and becomes 1 by lambda c square. So, this is another relation for guided wavelength lambda g, lambda naught and